Okay. So, today as I said yesterday, we will be first considering a decremental algorithm for strongly connected components, and then we will briefly outline the main idea behind how to extend it to get a decremental algorithm for transitive closure with the same update time. Okay. So, for this problem, what is the query? You are initially given a graph with m edges and n nodes, and the updates are delete an edge from the graph, and the query is given any two nodes u and v, are u and v in the same strongly connected component. Okay. So, let us start. Initially, in linear time, we can compute all the strongly connected components. Suppose we did that, and let us say, let us just number them like this. These are the strongly connected components. Okay. What is the first thing that comes to your mind? How are you going to maintain them under deletions? So, you can assume that say initially the graph has only one strongly connected components, right, because the algorithm, I mean maintaining the components here and here, they will be independent of each other.
So, keep a out BFS and into BFS.
Exactly, that is the most natural thing to do, right. So, if I just tell you that okay, let us consider an easier problem. In this easier problem, you are just asked to decide whether the graph consists of only one strongly connected component or not. Just yes or no, is the graph strongly connected? What will you do? Initially, you have checked that the graph is one strongly connected component. Just pick any node S and just maintain two BFS trees. Okay. A BFS tree rooted as this source S in this graph, and another BFS tree rooted at this source in the reverse graph, right. And then how will you decide? Initially, you can check, of course, that all the nodes will be part of both these two BFS trees, since this thing is strongly connected, and then suppose an edge u v gets deleted. What will you do? You will delete this edge u v from this BFS tree and the reverse edge from this BFS tree, and then you will check whether both u and v are still reachable from S in both these graphs. If yes, then it is still strongly connected, otherwise not. Is both. So, strongly connected means it should be connected in both these two graphs, right. Okay. So, for this scheme, how much will be the update time? And okay, and of course, once you see that after one edge deletion this is no longer strongly connected, you can just report it's no, and it will not remain strongly connected for the rest of the time because it is decremental. So, what is the total runtime for this? It's the runtime for the Evan-Shiller tree, right, and it's exactly O of m n. So, this is easy. Okay. Now, we need to answer this more general query. So, suppose we start with a strongly connected component. We had this source here, and after one edge deletion, suppose after we deleted this, C splits into multiple strongly connected components. Question: in undirected graph, if you remove one edge, how many components it can split into at most? 2. In a directed graph, is it going to be the case? No. Can you give an example? Exactly. Just consider this cycle. It is a very long cycle, and you just delete one edge from it, it just splits into n connected, strongly connected components. So, after this edge deletion, it can split into multiple strongly connected components. So, let us now say that this C splits into C 1 till C k. Without any loss of generality, suppose that this source S belongs to C 1. And let us say this graph induced by the nodes in C 1, let this be G 1, this is G 2, G k. So, first of all, we want to maintain a 2 BFS trees from S in G 1 now. This can be done, right, because you can find out this splitting in O of m time and then just go through all the edges, and whenever you see an edge going out of it or coming into it, you just delete it from these 2 BFS trees. Okay. So, in O order of m time, what can we figure out? We can figure out this BFS tree of S in G 1, BFS tree of S in G 1 reverse, and we can figure out these connected components C 1, C 2 till C k. So, we need to extend the same idea. So, we need to again pick a source node here C 2, a source node here for C 3 C k. So, that we will maintain 2 BFS trees in each of these components again. Now, which source node should we pick so as to minimize the runtime?
So we know that endpoint of the edge
Yes, we know the endpoint of this edge, but U and V, these two, there can be multiple strongly connected components, right. So, there will be strongly connected components, I mean
The previous BFS tree, whichever was at the top, maybe we can reuse that tree to get this tree. How does the BFS tree of G2 appear in the original BFS tree? Is it some, maybe is it connected or is it some contiguous subtree or something like that?
it will be difficult to say. It will be nice to say something about this, but I do not know.
but we have deleted just one edge, right?
Yes.
So then the tree in G2 should be a subtree of the original tree. Because so look at the subtree rooted at, so UV, right? Look at the subtree rooted at V. So then a part of that subtree goes into G2, right?
No, yeah, there is the problem. The problem is that these strongly connected components you do not know for sure. It's the nodes that appear in both these two trees. So, I actually do not know, I mean what to say to this, because say this was this one BFS, its source in the original graph, okay. This was in G, and now UV, this thing got deleted, right. You are saying that the subtree rooted at V, all these nodes will belong to one connected component? Not necessarily, right, because you have this condition that the nodes need to simultaneously belong to two different BFS trees, and we do not know how this BFS tree in GR looks like.
When you wrote C1, C2, CK, so are they some sort of topological order?
No. We are not maintaining the topological ordering. Good point. We are just maintaining the strongly connected components separately. Okay. Okay. So, let us try to think about this. When you are deleting the edges one after the other, what is happening? Just look at this initial source node S. Initially, it belonged to this giant component, then it belonged to a smaller component C1. Then might be after some time this component also splits and S becomes part of an even smaller component, and so on. What is the total time we are spending in maintaining the BFS trees from S? O of Mn. So, let us just look at this procedure. What will be the runtime? The runtime will be, first of all, to find these structures we are spending O of m time, but this split can occur at most n times, right, because at most you can get n strongly connected components. So, to find, so to recover from these splits, this basic step, it takes O of m n time.
We come to this step only after the guarantee that the SEC splits.
Yes.
SEC stays same, we don't do anything.
Yes, yes. So, this step, let us call this recover step, okay. This recover step, each time we do it, it takes m time, but we need to perform this recover step at most n times, because there are at most n nodes and there can be at most n strongly connected components, okay.
Each time you do this, the number of strongly connected
Component increases, so and it cannot go beyond n, okay. So, the total time spent on this recover is O of Mn, and now let us look at the total time we spend in maintaining these BFS trees from S. This is also Mn, right, because what is happening here, it is basically we are just doing eventuality on this. Total time on maintaining these two BFS trees. So, for the initial S, initially we started with an S, right, and why it is Mn? Because as long as this strongly connected component does not split, we are just maintaining eventuality from here, and during this recover step, what are we doing? We are just removing these edges that are going out of it ourselves. So, you can also treat that as an update in the eventuality data structure.
So, just one thing. So, when I am updating the tree of,
Yes.
so I have deleted an edge and I am updating this BFS tree. So, eventually I will note that a bunch of vertices in this tree are not reachable.
Yes.
So, then I will just construct a BFS tree on those guys and continue. So,
That is this step.
yeah. So, what I want to say is that I do this in G and I do this in GR, right? So I know that C2 to CK is made up of these unreachable things. That should work.
Unreachable in a strong.
In a strongly connected sense.
Yeah. So I have some unreachable vertices in G and in GR, right?
Hmm.
So the set of these, the union of
These two?
things cover C2 to CK.
Yes, exactly.
Okay. And what I want to do next is, so I just want to create new BFS tree starting from one of the vertices in this,
Yes.
but that will take longer than, okay, that will take order as the same.
Yes, I am going to come to that. But first, I am just trying to convince you during this recover step, before this recover step, you started with a BFS of S in G1, sorry, in G, in this original graph. After this recover step, you need to get a BFS in G1 on the graph induced by the nodes in C1. How will you get there? You will just delete all the edges that are not in C1. You can just go through them one after another. Okay? So, the total update time on maintaining these two BFS trees is going to be O of Mn. This just follows from Evan-Shiller tree. Now,
So another way of saying this, we can assume, kind of assume that the number of updates is just n.
number of updates is just M.
No, it's actually m, but n minus n of those will be like trivial updates, right? I mean, the actual updates which are non-trivial are only n. See, m minus n updates will be SCCs don't change. Only n updates will change the SCCs.
That depends on the sequence of deletion.
That depends on the sequence of deletions. So, by trivial and non-trivial update, what do you mean? So, we are maintaining, say look at this picture.
I'm just saying there are only n updates
Mhm.
which change the SCCs.
Yes,
That's all.
that is correct.
So the m minus n updates will not change. You'll spend only constant. No, you'll spend only m time on the other.
No, but you spend time maintaining the BFS tree. BFS tree, right? You have to rearrange things, saying which vertices.
Okay. So, let us be very clear about it. There are n updates in the original graph that changes the strongly connected components. Clear? However, after each such critical update, you might need to delete multiple edges from this BFS. Correct? However, in the end, overall you are deleting at most m edges from this BFS tree. Okay. So, for maintaining this BFS tree, you are just spending O of Mn time. Now, here comes the basic intuition. Suppose we were lucky enough that when this guy splits, okay, this thing split into C1, C2 till Ck. These connected components will be of varying sizes. When is the good case for us? The good case is if S belongs to the largest of these components, right? Because then you can reuse the, then you can just subsume the update time for maintaining that by just looking at maintaining this BFS tree data structure. Just consider a very special case. Each time that this tree splits, there is one huge component, subcomponent C1, and there is some other very tiny components. And suppose we are lucky enough that in each time step, this original source node S belongs to that huge subcomponent. Then you can roughly see that the total time should be O of Mn, right? Because it's just as if you are maintaining these two BFS trees.
So you say C1 is larger than sum of all the other.
I am just giving a high level intuition. I am just going to give you the exact algorithm later on. I am just saying that it's, if we can somehow ensure that this S belongs to the largest possible components, it's only helping us in bringing down the runtime. Do you see this intuition? Why? Because we have already taken care of maintaining these two BFS trees. Okay. But the problem is we do not know the sequence of edge deletions in advance. If you knew that, then of course you can carefully say that, oh, we need to pick this source node S so that it belongs to the largest component. But then it will no longer be dynamic because we know the sequence of edge deletion in advance. So, what is the simplest possible strategy that comes to your mind to address this issue? Sorry?
If multiple BFS3 and it's high probability one of them will be the largest component.
It's actually very close to what you said. You just pick the initial source node at random. Then you can see that, okay, these splits are determined in advance. I mean by your adversary, who is, these splits are determined by the sequence of edge deletions. They are deterministic, right? But if you pick the initial source node at random, and then if one of these subcomponents is huge, then with good enough probability that initial source node will carry over to the child subcomponent, huge subcomponent. Yes. So, that is why it is going to be a randomized algorithm. Did you follow this part? So, the algorithm will be you yes.
In the case that there is no such component which is huge than others are small, it can be that
All of them are even, right? Okay. That is where we will go into the analysis. I mean, what happens in that case? Right now, I am just giving you an intuition. It is not the formal proof. We will look at the formal proof. But did you get the intuition as to why it is, why the algorithm is like this? So, then what is the algorithm? You start with this giant component, pick a source node uniformly at random from all the nodes, start maintaining these two BFS trees. Then at some point of time, these things splits into k child components, and then this was the source node S. This source node S belongs to some component in C1. You keep maintaining the BFS trees from this source using these steps. And what will you do in these new subcomponents? Again, pick a random source node so that you can apply this argument recursively. This is just as simple as that. Yes.
So, okay, when we are doing this, right, how do we answer this query? Suppose we have a bunch of connected components with their BFS trees. So then I have to actually go over all the connected components, all the strongly connected components, and then find out where even we
For
are.
every vertex, keep the component ID or
Yes.
We'll keep it pointing.
Yes. That you can do, right? I mean, you are just maintaining these BFS trees. So, for each vertex, just keep a pointer to the source node of this BFS tree.
We go to the initial, I mean, what happens when an edge is deleted which does not change the SEC? Then we just change the particular BFS tree.
Yes.
Even 0
Yes.
we just change that.
Yes.
And how does analysis of that go? We have at most.
No, there are at most going to be at most m edge deletions. So, eventually tree takes mn time.
But it's over various even 0 trees.
No, there are, you are just maintaining two eventually trees, right? You are just talking about one component that does not change.
Okay. Okay, for a sequence of updates in one particular component, if there are some x, x edge deletions in a particular component, then we can we say that the time is x into n or something?
No, we cannot say that, but you have to look at the final total runtime on that. So, you are right, we cannot give this guarantee that, okay, these strongly connected components remains a component for x subsequent edge deletions. The update time for these two BFS trees will be x times n. We cannot give that guarantee, but the point is that overall the update time of maintaining these two BFS trees from a particular source will be mn.
So for an
Okay.
so it's like one eventual tree gets split into k eventual trees,
Yes.
but the analysis still goes through. I mean,
No. So, note that let us say this is event Shiloh tree corresponding to a particular source node S. Initially, this event Shiloh tree was a tree in this entire strongly connected component. Then this splits. All I am saying is that you can just reuse this information here.
So this entire chain, the total time will be mn.
Yes.
That is what we have.
Yes.
That's fine. But no, I'm asking about how in the other connected components.
You will just pick another random source node and start from scratch.
So in that, what about how much time is taken? I don't see how the analysis goes through for. I'm not convinced that the deleting edges when components don't change. That you said that entire time was mn.
All I said was just look at the two event Shiloh trees we are maintaining with respect to a source, particular source. Each event Shiloh tree is identified by its source. For each source we are maintaining exactly two event Shiloh trees. Just pick any source, look at these two event Shiloh trees, how much time we are spending on them. I just said that was mn.
We are not saying anything about the time taken for deleting like good edges. An edge is good if it doesn't break the SCC. An edge is good if deleting it doesn't break an SCC.
No, we are not. If you are asking me for a bound on the time spent on overall the deletion of only good edges, we are not giving that bound till now.
I thought you said that was mn.
No. All I meant was that maintaining this event Shiloh tree was mn. Okay. Now we need to give the analysis, but before we give the analysis, yes.
After the update only, we are choosing another source node, right?
Yes.
But didn't you say something like your randomization should not be dependent on your update or query?
No. That is okay. Here the update is given by the adversary, right?
If you remember that we had this replacement edge which we took dependent on our data set. The structure of the problem at some point, intermediate point, dependent on some randomization we did previously. That was the problem. But here there is no such.
I mean, an equivalent case would have arisen if it were the case that this source of randomization that we are doing, it is dependent on our previous choice of S. Then these two things might have been a problem, but it is not. I mean, our randomization just depends on the updates given to us by the adversary. Okay? And now, I will do the formal analysis, but before that I just wanted to go through the intuition. And before we do the formal analysis, it might also be nice to just write down the pseudocode. Okay. So, initialization. You just allocate an array of size n where ai will be the source node in a component that contains I. Okay. Then choose a random node W. Then you call this subroutine. This subroutine will build the Evan-Shiller trees. Okay. Next, what is this subroutine? Step 1, Ck of this graph GC 2 in each such strongly connected component Cj, where to do the following thing. Initialize Evan-Shiller tree data structures. So, this is in the reverse graph. And this is in the actual graph. And finally, we will see how it handles the update. And let me do this thing. Sorry?
Step B should be different for the component which contains the fluid from initializing the ESP data.
Okay, yes, it's initialize or adapt. Okay. And finally, how to handle the delete operation? The easiest case, if they belong to the different components. Then there is nothing to do. Otherwise, let this be the center in the concerned strongly connected components. containing u and v. So, this just says that if this edge is present in these two Evan-Shiller trees, any of these two Evan-Shiller trees, delete them, and then finally,
Why can it not be present? I mean, like, the update is an invalid update.
no, it's just a tree, right? Evan-Shiller tree is just a tree. There might be a non-tree edge from the strongly connected component that got deleted. Okay. So, if present, then just delete them, and finally, you need to check, right, that if it is still strongly connected or not. So, after this, if so, this case is interesting. So, this was this edge u v, and this is an original the normal graph g of c, the source was w. So, if this edge gets deleted and we see which in this is the out w tree, right. This is the Evan-Shiller tree in the normal graph without degrees. So, if u v gets deleted, we only need to check if v is still reachable from w. V is still reachable from w, right? Because u v got deleted and v is still reachable from w, that means every other node is still reachable from w. On the other hand, in the reverse graph, we need to check if u is still reachable from w. And if both these two conditions are satisfied, you can show that actually the strongly connected component remains the same. So, the only point is that just look at this out w, whether this tree got disconnected, for that you only need to check this node v. You do not need to visit all the nodes again, because if v is disconnected, then of course, the tree is disconnected. On the other hand, if v is connected, all of these children are still connected. Okay.
V is connected, aren't we maintaining the ES tree, so we need to maintain the layers around?
Yes, that will be taken care of within the ES tree, Evan-Shiller tree, right. That is the subroutine that we are using. Okay. So, if either this condition holds or this condition holds, then only we know that the components, strongly connected components got disconnected. That is, this means C splits. So, now you can check, this part is easy, right, what delete is doing. This is just working within one connected component, and now this condition says that this component splits. What will you do? Let us see what you are doing. Here you just run the static algorithm to find the children components, and then for each children component you just look, if the original source node was in that component, you just keep that as source, otherwise pick a random source and then just update or initialize the new Evan-Shiller tree data structures, and finally update these entries. Clear? Now, formal analysis. we saw the intuition, we saw the algorithm. What is the analysis? Let us look at this picture. This is some strongly connected component. It has m prime edges, n prime nodes. This was the source. This is Ck, and let us say that C1 has M1 N1 edges, this guy has Mk Nk edges. So, we know that N1 plus Nk is equal to N prime, and M1 plus Mk it's going to be less than or equal to M prime, right, because some cross edges might get deleted. Okay. Now, what is the computation cost that we have spent for maintaining this strongly connected component C? This is M prime plus N prime, right, because clear. Just for maintaining C, how much work did we perform? Because this is just two even Shilo trees. I am ignoring the factor 2 here. Now, let us just look at any component C I here. Anyone? What will be the answer? Mi Ni is definitely going to be an upper bound, okay, but it can be less than that. It is actually going to be an expected cost thing. Why? Because if we are lucky enough that this W appears here, then we have already taken care of that term above. And if we are unlucky that W does not appear here, then the cost is Mi times Ni. Clear? So, what is the expected cost? What is the probability that W does not appear here? No, it is going to be N prime minus, okay, it is the same thing, Ni divided by N prime times Mi Ni. Okay. We will see later on that it is okay if we just replace this Ni by N. Okay. So, just take this thing on faith. So, we can upper bound this cost by this. So, N is the upper bound on the number of nodes. Now, you can do two things. One is you can write a recursion. So, you got it upper bound on the total cost for maintaining this C1 to Ck, right. And you can write a recursion, I mean a function that depends on this m prime n prime in terms of these functions. Okay. But it is going to be slightly counterintuitive. So, it is probably better to look at what is happening inside this recursion. But before we go there, first note that these m values of n prime and m1 n1 to mk nk, they are fixed, they are deterministic, they are completely determined by the update sequence. Okay. Only these w's we are choosing randomly. Okay. So, this m n, they are not random, they are just fixed. So, now for the time being fixed an update sequence, so that you will know all these m prime n prime values, and then we are just going to analyze the cost. So, it seems the easier way to analyze this is the expected cost on Ci. We are just going to distribute this cost across the edges in Ci. So, as if each edge in the graph is getting some token, and if you add up all the tokens, you get the total computation cost. And then we are going to argue that the token received by each edge is not too much. Ideally, we would like to argue that it is not more than n. Okay. So, distribute this cost across the edges in Ci. What does this mean? Each edge in Ci gets minus Ni divided by n prime time n tokens in expectation. Okay. Now, let us try to analyze at the end of the algorithm what is the total amount of token that an edge gets. Okay. So, fix an edge E, and let us say that it looked like this initially. Now, I am using superscript here, okay, so that there is no confusion between that picture and this one. Initially, E belonged to this component C1, then this component split up, it was C2, it went like this till you reached Ck, and this is where it stopped, meaning E was deleted at this stage. And E does not belong to any child of this component Ck. And note that this sequence is determined in advance by the update sequence. This is not random, this is deterministic. Sanjukta, did you see what is?
I can see there why you are writing each area in CK gets this much of token.
So, this is the total expected cost for maintaining Ci. What are we going to do is, we are going to distribute this cost among the edges in Ci. So, there are mi edges in Ci. So, each edge will get this many tokens, and later on if we add up all the tokens, then we will get back the total cost. This is how we are going to argue about, and note that this sequence is fixed. Okay. Now, can anyone tell me from this analysis what is the total number of tokens that E receives during this algorithm, due to this algorithm?
What is happening here? E is deleted from CK, and this is the sequence of components that has been
Split. No, E is not deleted. Okay. Initially E belonged to C1, then you just trace the sequence of edge deletions. No, forward. Okay. And then what will happen after some point in time, C1 will split into multiple components, C2 is one of this child, and E belongs to C2, and it goes on for some time. We reach Ck, and then Ck splits, and we see that E is no longer part of any child of Ck. It can happen because of two reasons. One, the edge E was itself deleted at this point, or because E becomes a cross edge, right. It can happen because of these two things, but the point is that after this point E is not going to receive any more token, right, because it is no longer part of any strongly connected component. Now, I am asking what is the exact expression for the number of tokens E gets. It will of course depend on the size of these guys, right. So, note that in this number of tokens there is no m. So, it only depends on n. So, let us again say this is n 1. Oh, this is confusing. Okay. This is n 1, this size is say n 2. So, let us just write it down. When we go from C1 to C2, the number of additional tokens that this edge gets is n1 minus n2 divided by n1. I am going to write it down later on. Okay. I am going to take n common out, that is why we just had this upper bound. When we go from n2 to C2 to C3, the number of token it gets is n2 minus n3 divided by n2, and it goes on till we get to n k minus 1 minus n k n k. Sorry, times n, and plus, yes, the first term, right. The first term is again going to be no, that will be n 1. Yes, because
This is the pre-process.
no, yes, this is for the topmost strongly connected component, the eventual tree that you got. Okay, because the update time there will be m1 times n1 divided by m1. So, this is the total term. Okay, and this thing, this n1 is definitely less than or equal to n, right. So, I am just over counting, I am just going to write that this is at most this. Let us just look at this sum. Can you give a simple upper bound on this? One hint, you can think of, if you are familiar with it, think of the analysis for the approximation algorithm of set cover. This is actually a very common series. And the important thing here is that these guys are decreasing. I mean, you will need this thing crucially, that n 1 greater than n 2 and so on.
Change all the denominator to n1.
Sorry?
Change all the denominator to n1, you will get a telescope fixed, right?
Okay, you can change all the denominator to n 1. No, that won't do, right? Because then you will be undercounting. It is in the denominator, n 2 is smaller. So, if you change n 2 to n 1, it will decrease. Sorry? Okay, n k minus 1, okay, fine. Suppose you change it to n k minus 1, then what will you get above?
n1 minus nk by nk minus 1.
Yes, n 1 minus n k by n k minus 1, right? Now, n k and n k minus 1 can be very small. They can be 1 or 2. So, then what will you get? N, right, roughly, and there is a multiplicative factor n there. So, then you will get n square, but there are m edges. So, then your total number of token will be m n square, right. So, that is too much.
I think it is you n1, the first term you read as n1 plus n3 minus n3. So you should do something else. You basically did the harmonic series out.
Exactly, exactly. That is the trick, and it is a very common trick. You will see this used in multiple places. I mean, it is not the only place where you get to see this. Just look at this first term. What it says is, you are adding 1 over n1 minus n2 times. Okay. So, I can just upper bound it. So, n1 minus n2 times you are adding n1, 1 over n1. So, first time you add 1 over n1, the next time you add something more, you add 1 over n1 minus 1. The next time you add 1 over n1 minus 2 until you reach 1 over n2 plus 1. So, this whole thing is an upper bound on this quantity, right, because how many terms are there? n1 minus m2, the same number of terms, and the denominators here are only less. And then this term, again you do the same thing. So, you start with 1 over n2, sorry, yes, plus you go till 1 over n3 plus 1, and finally, in the last term you will end at 1 over n k minus 1 plus 1, I think, or something, times n plus n. And this quantity is at most log of n k, sorry, log of n1, right, because you can just upper bound this thing by saying 1 over n1 plus 1 times n plus n. So, you get n log n plus n. So, you can just say this is less than or equal to 2n log n. So, each edge in expectation gets 2n log n tokens. There are m edges. So, what is the total update time? Mn log n. We wanted to get mn time, we settled for something slightly worse, just mn log n, 1 log n factor worse. You can actually get an mn time bound if you write a crazy recursion on this, but exactly the same algorithm, not crazy recursion, some recursion, and it works out to be mn, it is there in the paper. So, I am presenting this thing from a different paper, but I found this to be more insightful than just writing one recursion and
This is the Fox paper,
yes.
and what you're presenting is from a different.
Yes, it's from a very recent paper in Stock 2013. It's a different analysis, but I found it more insightful. Instead of just writing down a recursion and proving it by induction, you can just see what's going on here. Okay. So, this is done. Now, let us consider, okay, actually I will erase it later on. Okay. See, the main idea is this. Yes.
So just the first advice we could do is try, if suppose C1 was the largest component, you'll try to make C1 very sparse, say just a tree, and make the other k-1 thing clicks. So those things have, so mi squared, mi will be ni squared for I greater than 1 and m1 equal to n1. So if we can do this like in every step, so he kind of ensure that each edge, what I'm trying to do is like trying to increase the number of times an edge splits, like goes into a different component.
I agree. So, I think the worst thing would be one, that the number of nodes are the same from C1 to Ck, so that the random thing does not get anything. Oh, okay. Even then there is a problem. Say the number of nodes are the same, okay, and then there is exactly one thing Ci that is very sparse and the others are cliques. Again you can see that with high probability this W will end up in one of those cliques.
No, W is dependent on the randomization dependent on nodes.
Yes.
So oh.
You see. So, this algorithm is actually quite clever. I mean,
But if all the components are evenly sparse,
hmm.
even size, equal size, then
Okay, so the main point is each edge getting a token is independent of mi.
Yes.
It's only dependent on
Yes.
mi.
Yes. So, this is one of those algorithms where which is you can just state it in 3 lines, but it's actually quite nice.
So the bad thing is when NIs are much smaller, is that
No, then the NIs have to sum up to n prime.
right? No, what I mean is, so you made a statement that if the vertex W goes to the largest back among its C1 to Ck, then it's better for us. So I'm just trying to see that.
No, okay. The thing is, if the NIs are very small, see that is the point. Suppose the NIs are very small, then
Sequence will terminate.
yes, exactly. The NIs are very small, then this guy is getting n tokens here, but it cannot go on very long. On the other hand, if the NIs are large, then this guy is getting small number of tokens. Yes. So, Arjun, you will be presenting the de-randomization of this thing next week. Okay.
So the de-randomized version runs in the same.
I do not know. I have not read the Arjun will read it for me, present it for me. If you have to ask Arjun. Okay. So, okay. Any other question about this? Okay, then let us move on to transitive closure. I will just outline the basic approach, will not give the entire algorithm, unlike this one where I gave all the details. We want to maintain transitive closure. So, basically that means we need to maintain this DAG on the meta graph, right. So, basically if these are the connected components and then look at this DAG between these connected components as we discussed last week, and we need to maintain this DAG.
So, why can't we use the previous algorithm to do?
The previous algorithm does not maintain these edges, these cross edges.
We used a subroutine find the strongly connected components of the given set of nodes. So that returns to DAG.
Okay, you have partially given the answer, almost fully. The main idea is this, and I am basically restating what you are saying, but in slightly different way. Okay. The previous algorithm only were maintaining these sets, okay, these sets. Now you have a DAG defined on these sets. So, the first thing to check is what is the update time for transitive closure on a DAG first. Forget about this meta graph thing. You start with a directed acyclic graph and I just delete edges one after another. Can you maintain the transitive closure? Okay. We will show that we can do that in O of mn time, and then we know we can how to maintain these sets in mn time. So, we can just combine these two things. Okay. The detail that will be missing is as follows. I mean, these guys can split as well, right. So, I am just going to give you an algorithm for maintaining transitive closure in a DAG, but that algorithm does not take care of these nodes splitting into multiple nodes. That is one additional detail that will be missing, but you can see the main idea. Okay. So, the first thing is decremental all pair reachability in a directed acyclic graph. This thing will actually follow if we can show So, if you just maintain a reachability tree, if you can suppose you are just given a sources, you are asked to maintain a reachability tree from that source. If you can maintain that in m time, you can solve all pairs reachability in mn time, right. Simply run this algorithm once for each source and there will be n sources. Okay. We can solve this using an event Schiller tree, but that will take mn time, too long, too much for us. We can show that for DAG it actually can be done much faster. So, now we are just solving this problem here. So, suppose the source node is S, we want a reachability tree, maintain a reachability tree. Okay. So, somewhere down the line this edge u v got deleted. And what we need to do is, we need to find is there is any other incoming edge from V from one of these parents. Note first this difference, that here we are not going to maintain a shortest path tree, we are not going to maintain a BFS tree, unlike in Evan-Shiloh tree. We will just maintain some reachability tree that hits all the nodes that are reachable from S. Now, can you just think about it for 2 minutes and tell me what is so special about DAGs that this problem is much easier? So, u v got deleted and you need to fix V, and potentially you might need to fix V's children as well if they are not reachable.
Some children of V cannot become the parent of V.
Exactly, that is by definition. So, you cannot have an edge like this, then it would not be a DAG. So, all the incoming edges to V are either from some other regions of the tree. I mean, there can be an incoming edge like this, or there can be an incoming edge like this, or they are from some nodes that are outside the tree. So, this guy is bad node, say V prime, it is not reachable from S, but it has an incoming edge. Okay. If we find an incoming edge to V from some part here, say V double prime, then you can just make V double prime a parent of V, and we will still get a reachability tree. Okay. Otherwise, if there is no incoming edge from these other regions of the tree, then we know that V is unreachable. We will take V out, and then we will make each of V's children dirty as before, and do the same thing for each of these children. Okay. Now, here is the idea. For each node V, just partition the incoming edges, okay, into 3 parts. One is parent of V, this is the parent of V in the tree if it exists. Otherwise, we say that it is probed, these edges have already been probed. And these edges have not been probed. Then,
These are the in edges.
yes, these are the in edges. Okay. Now, the guarantee will be that each edge in probed V is not reachable from S. So, each U in probed V, so they are useless. Sorry, initially probed V is empty. When you start, we will be probing these edges after this parent edge gets deleted, right. So, at the start of the algorithm, each node V has its parent and all the other incoming edges are unprobed. And then when if its parent gets deleted, we start probing the unprobed edges and move them to the set probed. Clear? At 1:30, okay, I will finish it within 10 minutes. Okay. Each probed V is not reachable from S. And then how to fix this edge deletion? I am just writing it very fast. Okay? You are just fixing this thing, delete UV. So, scan through the edges, nodes in unprobed V. Suppose you are at this guy. If U belongs to this tree, you can just check it, right, whether U is valid or not. Each node can store a pointer. Then make U the parent of V, and delete U from unprobed V, and the tree is fixed. Otherwise, delete U from unprobed V, add U to probed V, right, because U is no longer is not reachable from S, you have decided. And after this scan, if you fail to find a parent, if the scan fails, when the scan fails, the list unprobed V is empty, right, there is no other unprobed node. Then what you do? Set you have this counter, set this thing to false, make each child of V dirty, and you have this while loop. You just get back here.
So sequence in which we process the dirty nodes doesn't matter.
No, okay, again, the sequence here will matter as well. No, the sequence in which we process the dirty nodes does not matter, because here the layers do not mean anything. Previously, the layers meant the distances. Yes, and you can see that, I mean, why the total update time will be order of m, because each time you are probing an edge, you are just moving it to the probed list, and you are not going to look back at it anymore. Okay. No, they are actually, what they do is that this is from a previous paper. What they do is that they combine this algorithm with their own strongly connected components algorithm to get here. As I said, there is one detail that is missing. How do you take into account that the nodes are splitting in this stack, but that can also be taken into account. Okay, so we can stop here.